All right, well, I will get started with a word of prayer. Ahem. Ahem. Dear Father, we thank you for this day. Thank you for this class. Just ask you to be with us today. Help us to understand the material together. And I just pray that we would glorify you what we do and just learn a little bit more about matrices today. In the name I pray, Lord Jesus. Amen. Okay, so let me get into it here. So this is my lecture 6, if you're counting, and I am. And I've entitled this Matrices with a Particular Set of Skills, which is a very silly title, but that's what I got. And so I'm going to begin with just a rehash of some, special kinds of matrices we've talked about, right? So like, let's see here. IN, that's something we talked about. So IN is E1, E2, EN, right? This is a n by n matrix. This is called the identity matrix, right? And so for instance, I2 is a 2 by 2 matrix. It's 1, 0, 0, 1. And I3 is 1, 0, 0, 0, 1, 0, 0, 0, 1, right? These are all identity matrices, right? So, and generically speaking, if I just write I like that in this course, it's understood to be the identity matrix of the appropriate size for the formula to make sense, right? It's like I don't always write the sub n on the identity matrix. I've also talked a fair amount about like the matrix units, right? So this is the identity matrix. We also talked about matrix units, which is a kind of funny term in the sense that they're not, like sometimes we use the word unit to mean something has a multiplicative inverse, but these are not like that. Like these matrices cannot be inverted, all right? They don't even have to be square. Like we could talk about a rectangular and matrix unit. And the definition for this one is that if we look at the kth component, we can write it as Kronecker delta ik, Kronecker delta jl, which is just a fancy way of saying it's 1 if I is equal to k and j is equal to l, and it's 0 otherwise, right? So like, for an example, E23, it could mean 0, 0, 0, 0, 0, 1, which would be, of course, a 2 by 3 matrix, right? But of course, it could be, it could be a 3 by 3 matrix, which has got an additional row of zeros. It just depends on context, what's the meaning of E23. So like the matrix units and the identity matrix, these are notations which we use in a variety of contexts, always with the same meaning, but they could have different size, Zero matrix is also like this, right? How big is 0? It could be a 2 by 2, it could be 3 by 3, it could be 2 by 3. I mean, we let 0 be what it needs to be to make sense. We also have symmetric matrices and anti-symmetric matrices. What do those look like? How do we define those? Symmetric means that A transpose is equal to A. Anti-symmetric means that A transpose is minus A, right? I showed you guys that any square matrix can be written as a sum of an anti-symmetric and a symmetric matrix. There's like a standard trick to do that. All right, so we also talked about, upper triangular, which, is something of the form, let's say A, B, C, D, E, F, like that, right? Or we could talk about like strictly upper triangular. What would the difference be? An example of that would be what? If it's also a 3 by 3, what would it be like? Just something like, let me put numbers in this time. It's like 0, 1, 2, 0, 3, 0. That would be an example of a strictly upper triangular matrix, right? So here's our default our default custom in here, which I should mention, is that if I don't write entries, what are those entries? 0, right. So like what's left unwritten here are zeros. Now some people will like make like a big 0 over there, and sometimes I'll put in zeros and dot dot dots, but I don't need to. Like I could write less, just like that. All right. One exception to that rule is I pretty much do write the numbers when I'm doing row reductions. Like I don't, if I've got a row of zeros, I just write them. I mean, I know other professors who, like when they teach row reduction, professors that are not here, but you know, they'll like, once they have a row of zeros, they just stop writing that row. And that's not a wrong idea, you know? It's just I don't do that for the sake of just being super explicit about how matrix, you know, operations work. There's also like lower triangular, right? And those look like, you know, A, B, C, D, E, F, and like that, right? And of course you've got strictly lower, which is what? Strictly lower triangular means what? Something like, I'll do a 4x4. 0, 0, 0, 0, 1, 2, 3, 4, 5, 6. This would be an example of a strictly lower triangular matrix, right? Any questions? Like, this is just name calling at the moment, right? That would have been a strike, but I'm not calling them yet. But it would be. Just saying. Starting next week. All right, so, and then another important example we'll be using some today is the notation n sub k, which is a k by k matrix where like n sub k, I think it's probably best for me just to write it this way, like n sub k 1, 2 is equal to n sub k 2, 3, all right, and so forth and so on until we get to the k minus 1 kth spot of n sub k. And these are all 1. This is a really like important example matrix. Like it's got really neat properties, and it's nice to talk about and have a standard notation for. So for instance, n sub 2 is a 2 by 2 matrix, and what I mean by that is simply this. All right? What's n sub 2 squared? Try multiplying this matrix by itself. We get 0 for the first column. Right? What happens when you do n sub 2 times n sub 2? Think about it. You're doing like E2 times this, E1 times that goes in the second. So anyway, you get 0. N sub 3 is a 3 by 3 matrix. It's got 1s on what's called the superdiagonal. The superdiagonal is the diagonal entries, like, well, okay, technically not diagonal. It's a diagonal of entries, but it's right above the actual diagonal, right? The 1, 1, 2, 2, 3, 3 spots. So this is n sub 3. What happens when you square it? Oopsie. Let's see here. So the first column is zeros, right? And I multiply this over there. That picks out E2. E2 is just, excuse me, my bad. That picks out E1, which is just 0. So the second column is 0. And then I've got 1, 0, 0 for the last. That's the square. What happens when you calculate the cube? So n sub 3 cubed is actually equal to 0. All right. So this is the so-called nilpotent matrix. And I would say it's the nilpotent matrix of order k. I mean, generically speaking, if you have a matrix, right, which the cube of the matrix is 0, yet the second power is non-zero, that would be a nilpotent matrix. I say this is the nilpotent matrix because it's like the standard one, right? Just put ones in the superdiagonal. If you study, though, like this strictly upper triangular matrix, if you cube this thing, it's also, I think, going to work out to 0. So like strictly upper triangular or strictly lower triangular matrices, I think also are actually nilpotent. You can check me on that, but anyway. There's one other like special idea about matrices we talked about, which was what? Remember? We said that given square matrix, right? A, we say A is invertible with inverse A inverse provided what? What condition do we have? What has to hold? Two of them actually, right? A times A inverse is equal to the identity, but that's also equal to A inverse times A, right? So that's the inverse of a matrix. Right. It turns out the theory will prove for us actually that you could either take like the left or the right equation. Either one suffices to prove the other actually. All right? We'll eventually like give arguments for that, but for now you can just rest assured that if we checked either one of those being true for a given matrix, like actually that would suffice. It's enough. Anyway, any questions? And that's just a quick review of like some of our basic terms. All right, well. So with that, I'm going to talk to you guys about block multiplication. So block multiplication. Now, we've actually seen a special instance of this already in like the column by column multiplication rule, right? So we talked about that. I say we, but I mean I talked about that in the video you guys were supposed to have watched. I guess I'll find out whether or not you watched them when I give a test, but no, you've watched them. What am I talking about? Of course you watched them. All right, so, but I don't know. That's always the consternation of like snow days and such. It's like you post a video, but like, what does that mean? You know, I don't know. Anyway, so like block multiplication concerns if you have like matrices where you have a way of parsing the matrix into like submatrices of matching sizes. So like the simplest example, besides like the column by column multiplication we already talked about, would be something like this. If I have A, B, C, D like this, and I multiply by X, Y, Z, W like that, right? So here, I mean that A, B, C, D, X, it's like here, A, B, C, D, X, Y, Z, and W. These are actually all n by n matrices. Not numbers, but matrices. It turns out that you can multiply matrices like this, simply behaving as if the matrices A, B, C, D, X, Y, Z, W are themselves numbers. But you have to maintain the order. So like, we know how to multiply matrices, right? So we've got A times X plus B times Z. So it's important that the A goes first, and it's important that the B goes first because they're in the left matrix. The matrix multiplication doesn't commute, as we learned, right? So it matters which order things are in. That's the proper order. Down here, I've got CX plus DZ. all right? And then over here, I've got what? I've got AY plus BW, right? And what? CZ? Oh, wait a minute. CY, I can't. Duh. CY, right? CY and D plus DW. This is what I mean by block multiplication. It's if you've got a way of like parsing your matrix into blocks such that you can multiply the blocks as if they're numbers. This is block multiplication. I would say in some sense, remember the column by column rule we had? So if we have like A times B1, B2, Bn, I told you guys that in fact that's the same as AB1, AB2, ABN. That's kind of a block multiplication type rule, right? It's saying that a matrix times a concatenation of columns behaves the same way. It's just like scalar multiplication, right? How do you multiply, scalar multiply a matrix? You just multiply every entry, right? So in some sense, that's a kind of block multiplication. Okay, so like, who cares, right? Well, you should care. This is a way to make easy test questions, like super easy test questions, like this. Suppose you want to find the inverse of 3, 1, 3, 2, 1, 1, 7, 8. All right, and I'm going to actually write the zeros in just to be explicit here. Again, I don't technically need to write them, but they're there. So I can invert, actually, this block matrix, right? This is a block matrix. It's a 4 by 4 matrix, but made from 4 2 by 2 blocks, right? And it turns out, and we'll check, right? But I can just invert the blocks, actually. And you guys remember the 2 by 2 inverse formula? I'll write it up here. We have A, B, C, D. Inverse is, what was it? It was 1 over AD minus BC. Flip the diagonals, put minuses on the off diagonals. And we proved that that matrix actually is the inverse for the 2 by 2, right? You multiplied it by itself, got back to the identity, the 2 by 2 identity. So look, for both of these matrices, I have, oh, wait a minute. I think I might have copied that down wrong. Just a second here. 2, 1, 3, 2. 2. Oh, yeah, I'm sorry. That upper 3 was a 2. Otherwise, we got fractions. We don't want fractions. It's too early for fractions. Let's put a 2 there. If I put a 2 there, things are ever so nice. Because if I do that, 2 times 2 is 4. 4 minus 3 is 1, right? And over here, 1 times 8 minus 1 times 7 is 1. So like the fraction is 1 for both of these 2 by 2 matrices, which just makes it a little bit easier to follow, right? And so all I have to do then is follow the rule, flip the diagonals, which is kind of a non-event for the upper square, right? Minuses on the off diagonal, minus 1, minus 3. I keep my zeros elsewhere, which I'll not even bother writing down. Down here, I flip my 8 and my 1. I put a minus 1 and a minus 7. So my claim is that if this is the matrix we're inverting, this is actually formula for M inverse. Right. And you can try it out, right? Like, try it out. If I take the matrix 2, 3, 0, 0, 1, 2, 0, 0, 0, 0, 1, 7, 0, 0, 1, 8, and we multiply that matrix, right, by my alleged inverse there, 2, minus 1, minus 3, 2, zeros below, zeros in the upper block here, and then 8, minus 1 minus 7, 1. What happens? Let's see here. That times that, we get 4 times, like we get 2 times 2, which is 4, minus 3, which is 4 minus 3, which is 1, right? So I get 1 here. And then look what happens when you multiply this first column times the second row. You get 6 minus 6, which is 0 plus 0 plus 0, so you get 0. And then, of course, when I take this first column and I multiply by the third or the fourth row, I just hit zeros. Ka-chunk, ka-chunk, right? So it's just 0 added to itself 4 times. So I get 0, and I get 0 here. And if you continue down this path, you multiply it out, you should see that what you get is the 4 by 4 identity matrix, right? Which proves, of course, that that is actually the inverse, right? But let's look at this. Okay, fine, this is I4, right? But what's another way to look at this? We can look at this as I2 and I2 like that, right? Now, it's nice to have a notation. It's nice to have a notation which reflects these patterns we're seeing, all right? So one of the notations that we'll start using is to say that this is equal to I2 direct sum I2. So this circle with a plus in it is the direct sum, or Kronecker sum. So when we take the direct sum of two matrices, we get a bigger matrix, where that bigger matrix has the matrices we're direct summing on the diagonal. It's what's called a block diagonal matrix. This is a block diagonal matrix because only the blocks are non-zero. See the off? Right? You guys remember what diagonal matrix meant, right? It means we just have non-zero on the diagonal. A block diagonal just has blocks which are non-zero, and the off diagonal blocks are 0. It's a block diagonal matrix. All right? Anyway, before I get into that full bore, let me give you one more example of block multiplication. So example 3. You could have, I mean, it doesn't have to be square is my point. You could have like this, A11, A12, A31, A12, A22, A32. I'm just numbering the blocks so that I can like follow the pattern easily. B11. Of course, this is also how we 2-1 there. How we number components, right? And the thing is, if those are all matrices of appropriate size, and like we can talk about this, what does it take for them? What do I mean by appropriate size? I mean, they have to be, let's say, multipliable. Like there doesn't seem to be a standard word, as far as I know, like in linear algebra for when two matrices can be multiplied. Some people say they're conformable. I like to say they're multipliable because it just sounds right to me, but there doesn't seem to be wide agreement on what the terminology is. But all I'm saying is like, okay, so like I write it down. I've got A11, right? What should I be expecting? I've got a 3 by 2 blocks and a 1 by 2, a 2 by 1 block. So I should be expecting a 3 by 1 block, I think here. So I've got A11 times B11 plus A12 times B21, right? What's my next block? How about A12, right? Times B11 plus A22 times B21. This should be totally unsurprising, right? If you're up to speed with your matrix multiplication. Now, if you're not up to speed with your matrix multiplication, well, then I guess this is a misery. But like you need to fix matrix multiplication soon. It's not going away. It will be with us the rest of the course for sure. Yeah. Oh no. Yes. Oh man. So yes. I wonder what else I've done. I'll make the corrections red. So 2, 1, yes. I think it also happened over here, didn't it? Yeah. Okay, I think we're good now. All right. Okay. So we could say something like, you know, so here's like a possible way of running this down. A1 should be like M1 by N1. A11. A21, it should be M2 by N1. A31 should be M3 by N1. Do you see why they have to have the same N1? All the A11, A21, and A31 blocks? Why is that? They're stacked over each other, right? So they must have the same number of columns to match up, right? So I don't have the freedom to write this and then make a different number here. Like they have to have the same size, same number of columns, but they could have different numbers of rows, okay? And how about then, with that, what are the possible sizes of like A12, A22, A32? Those are gonna be what, like? Well, they match up row-wise, right? You got no freedom in the matter. How many rows have to be in A12? If I said A11 has M1 by N1 matrix, this has to be what? It has to have the same number of rows as the A11, right? So this has to be M1 by, I mean, the number of columns over here could be different, so we could say by N2, all right? However, once I write N2 for the number of columns of the top block, I am stuck with it for the other two I haven't written yet, right? In fact, these have to be like, you know, once I write what I've written, logic demands that I put M2 by N2 here and M3 by N2 here, right? Okay, so how about the B11 and B21? How big should those be? I mean, some of this is non-negotiable, right? Like, what's non-negotiable? In order for these products to be defined, we need what? The number of rows in the B matrices to map the number of columns in the A matrices, right? Because that's the way matrix multiplication works. There has to be a matching, right? Like B1 has to match these guys, right? So it has to be like N1, that was supposed to be an N, as in N1 times something, and B2, non-negotiable, has to be N2 times something. Now, how big are the somethings? Like, we could say this one's P by P. It's got P columns. B11's got P columns, right? Once I write that, though, I'm forced to say that the other one also has P columns, right? Because they share the same number of columns. So this is a what? We've got a, we're dealing with an M1 plus M2 plus M3 by what matrix? By N1 plus N2 matrix. And it's giving us a what? It's giving us a, my bad, I times a, I'm an idiot. So this is the, this is the A matrix. What's the size of the B matrix? It's a what? It's a N1 plus N2 by what matrix? N1 plus N2 rows, P columns, right? So these have to match up in order for the matrix, you know, the larger, let me just call this whole thing A, and this whole thing I'm talking about B, in the sense of this being, this all together is A, and this all together is B, all right? So AB is a matrix. What's the size of AB? AB is an element of our what? M1 plus M2 plus M3 by what? By P, right? I hope this has been a long enough discussion of this that you understand what is involved in making the blocks match up, all right? If you look at my typed notes, I even have a notation there to reflect this in terms of using like a sort of stratified index notation where I have different kinds of indices for different blocks. This sort of notation is used in physics where we use a different index type to indicate different sub-objects, all right? Like some people might write a 4-component vector, something like this, like psi alpha dot. So each one of these is a 2-component vector, and it's altogether a 4-component vector, but they'll use like an alpha for the first 2 components and an alpha dot for the second 2 components. This is something like the wave function of an electron has something like this. It's called a spinor. Anyway, that doesn't matter in here. Just saying. Well, anyway, are we clear on what block multiplication is? I think I said enough. What's more important than the block multiplication is the language of block diagonal. Like block diagonal is really where it's at. We should define that carefully and notice that block diagonal matrices allow an arithmetic which makes life much easier. Like we can sort of just operate symbolically at the matrix level, and we don't actually have to write out these giant matrices. Like I can do a calculation with block notation of like a 20 by 20 matrix. Like we could calculate things about a 20 by 20 matrix and not even flinch. Like it would be easy once we understand how the matrix works. Now, if this is only really what my claim is only bold for like the most nice kind of matrix, which I would say is a block diagonal matrix. Well, that's not entirely fair. What's even nicer than a block diagonal matrix is just a diagonal matrix, right? What's a diagonal matrix? Yeah.
Matrix composed of wave elements in the n slot.
Only in the a sub n slot.
Assuming A is in matrix.
So let's say a sub I slot, but I'm right there with you. I tend to use n for like the size of a matrix. I try not to use n as an index in here, which is not true for other courses, fair enough. You know, like Calculus 2, for example, we use n as an index a lot, right? So, but you're right. So, you know, for example, what example am I on? I don't know. 4. Oh, okay. So let's say 3.5. So if I had 1, 2, 3, right, and I was multiplying that by 4, 5, 6, and everything else is 0, how do you multiply diagonal matrices? If you do it, you just do 1 times 4, 2 times 5, 3 times 6. That's how they multiply. So like multiplying diagonal matrices is stupidly easy. All right? That's how diagonal matrices multiply. So, definition here. For A in our M1 by M1, and I meant A1, A2 in our M2 by M2. So these are both square matrices, not necessarily the same size. We write A1 direct sum A2 to be the block matrix, which has the form that, right? This is an element of what? How big is this matrix? It's a M1 plus M2 by M1 plus M2 matrix, right? such a matrix is said to be block diagonal. This is a block diagonal matrix. Right? And so like we can continue this, likewise. For A1, A2, A sub k, all square, without burying you in a list of indices, like matrix sizes, I think we can just write out the pattern, right? The way this looks is there's an A1 in the upper block, right? And then you've got an A2 here, and so forth and so on, until finally you get to A sub k down there. It's again a square matrix where only the blocks are non-zero, and all the off-diagonal blocks are 0. This is, again, a block diagonal matrix. All right? So if a matrix is the direct sum of square submatrices, for some set of square matrices, then M is said to be in block diagonal form. All right? And there's a theorem that I should share with you guys. It's super easy to learn. I'm not going to prove it if you guys don't, if you can forgive me. But, given M, well, I guess I said A, my bad. A equal to A1, direct sum A2, direct sum, suppose it's got k blocks, right? And B equal to B1, direct sum B2, direct sum BK, right? So suppose A and B are both block diagonal matrices, all right? And suppose that all of the blocks have like matching size, all right? Every block is matchy-matchy. What happens when you multiply A and B? How does that work? A times B, right, is simply equal to A1, B1, parentheses, direct sum A1, B2, A2, B2, direct sum, AK, BK. In other words, the product of two block diagonal matrices is simply a block diagonal matrix where each block is formed by a product of the blocks of that position, right? It's just like how we multiply diagonal matrices. Just multiply the diagonals. Just multiply the blocks. But these are matrix multiplications, right? And so, also, what's the deal? If you take a to the nth power, how's that going to work? What happens when you multiply the matrix by itself? You just get the square of the first block, the square of the second block, all the way out to the square of the kth block, right? Continue this pattern. The nth power of a block diagonal matrix is simply the block diagonal matrix where each block is raised to the nth power. Like that. Yes, sir.
Is there a notation for like an opposite direct sum?
An opposite direct sum for like the off diagonal blocks? No, not that I know of. Well, not in my writing, but I mean, listen, this is as far as I go into the like the block nomenclature. There's a whole world of deeper formulas. If you look at the book, I think it's Gullub. It's maybe something. I think Gullub's one of the authors. There's like a standard graduate numerical, perhaps. Well, anyway, it's a deeper matrix theory book, and it's got all kinds of further calculations about blocks in terms of like taking a matrix and ripping it apart into vectors and all kinds of things we don't cover in here. So I covered like the most basic aspect of the block multiplication here, but that's, trust me, this will be plenty for us to play with. And it serves the main storyline of the course, actually. So we'll use this notation in the formulation of some of the more interesting theorems that we get to later. For now, it's just like it's a nice, clean, crisp way of building bigger matrices from smaller matrices, right? Like, for example, let me show you the power of the method, and at the same time sort of undo the goodness of the method in the same example, all right? So here's the power of the method. Example 4, I can talk about I2, direct sum, N3, right? That is a what by what matrix? Right? So explicitly, this is what? Going back to the start of today, right? What happens when you square this matrix? You get I3 squared, direct sum N3 squared. What happens when you cube the matrix? We get I3 squared cubed, direct sum with N3 cubed. What's N3 cubed, though? What's by the way, so I can simplify these, if you like. This is, of course, just I3 direct sum, E13. This one here is I3 direct sum, the 3 by 3 zero matrix, if you like. I guess I could call it O sub 3 if I want a notation for it. All right, and again, just to undo the goodness, I'll write it out. 1, 1, 1, 0. Oh, I can't. Oh man, how did that become a 3? Dudes, don't let me do this. This is what? I sub 2? Does it magically become I sub 3 over here? No. This is a what? 2. Good grief. 2. All right. So sorry. Fixing. So this first one is 1001. E13, I'm talking about this one. First row, third column, it's a 3 by 3 matrix. It's like, there you go. This one here, of course, is just I with zeros elsewhere. Do you notice, like, my larger point is we didn't actually have to do 5 by 5 matrix multiplication to come to these understandings. We could just study the structure of the block separately and, like, put it together. I'm just writing out the 5 by 5 to illustrate, like, what's hidden in the more brief note. This is very, very useful in terms of, like, well, it's not, it's useful in as much as the matrix allows for this kind of analysis, right? Here, let me show you a few. As usual, time has gotten away from me. There is one other kind of matrix I wanted to talk about today, which is a so-called elementary matrix. Now, we're just starting the conversation today. We'll finish it, like, hopefully next class. But elementary matrices are matrices which correspond to, oh man, the scanner sends things to Gmail for me, and I almost always have a Gmail window open. There it is. All right. Go away. So as usual, I will post this, right? And we've covered most of it. but like the last, I think, maybe 2 pages or so, I haven't. But the idea of the calculation, I just want you to look at the idea of the calculation with me. You don't have to write this down today. It would be good for you to, like, you know, read the notes after class and think about them. So first of all, I have, you know, a few more representative calculations here in terms of block multiplication. By the way, a diagonal matrix is block diagonal. It's just kind of a dumb block diagonal matrix, right? A diagonal matrix is a block diagonal matrix where all the blocks are 1 by 1s. So it's kind of silly, but that counts. Notice that if you just have 2 blocks, right? If they're both invertible, the idea of my, like, second example, I think, it generalizes. Like, you could just invert the blocks, right? One at a time, and so this is going to be the inverse of that. Provided both blocks are invertible, the correct sum of them is invertible like that. So, the last thing I want to talk to you guys today is the idea of an elementary matrix. An elementary matrix is a matrix which accomplishes a row reduction. All right? So like here, I do row 1 minus row 2, right? Down here, I take the 2 by 2 identity, and I do row 1 minus row 2. That brings me to this matrix. We call that E for elementary matrix. If I take this matrix times A, what happens? The same row operation. So by doing the row operation to the identity matrix, that gives us a matrix that accomplishes the row operation. This doesn't just work for row addition, it also works for row swapping. Like row 1 swap row 3, like so. Now we're dealing with 3 by 3 matrices. I do it for the identity, 3 by 3 identity. Swap-a-roo, rows 1 and 3. Gets me to here. Take that matrix times the matrix which is given. Swaps rows 1 and 3. Not an accident, right? So there's a general theorem to see here, which is that if you have A, row reduces to R through some elementary row operation, then if you take E to be defined by taking the identity matrix of the appropriate size, right? So that these are multipliable, right? If A is M by N, that means that E has to be an M by M, as in mommy by mommy elementary matrix. But you just do that same row operation to the identity matrix, and that, when you multiply on the left, like so, will do the same row operation to the matrix. You're like, why are you doing this? You're taking something I understand and making it into something I only partly understand, depending on where you are with matrix multiplication, right? But this you can scaffold, you can keep doing. If we have, you know, this matrix A, row reduces to the identity matrix through these 1, 2, 3, 4 row operations. If I do those same 4 row operations to the identity matrix, it gives me these elementary matrices, E1, E2, E3, E4. All right? And so what that means then, if you follow me, is that if I multiply A first by E1, then by E2, then by E3, then by E4, that's the same as doing row operations 1, then 2, then 3, then 4, which takes me from A to the 3 by 3 identity matrix. But hey, what does this mean? This means that A is invertible, and that the inverse is in fact this cofactor of A, this left factor here that multiplies by identity. In fact, this product of elementary matrices must be the inverse of A, which is kind of weird, right? Maybe you didn't see that coming. I certainly wouldn't have seen that coming if I was sitting in your chair. But that's the truth. We can take the elementary matrices and multiply them out, which is, by the way, a pain in the butt. I made like 4 arithmetic mistakes I had to fix if you look at the whiteout. But after some finagling, I get to this as the inverse, and then I check my work, this times that, and I get that. Therefore, the inverse is in fact E, where E is the product of these 4 elementary matrices. So, what this all means, next class, is we can investigate how we can think about row reduction instead as matrix multiplication by these elementary matrices, which of course have a particular set of skills. namely row operations. Anyway, I shut up. Thanks, guys.